Hello, thank you for joining. My name is Siddhartha Banerjee. Thank you again for joining. I'm going to present to you an open source technical computing platform to analyze Converge CFD results. So a little bit of background of what I'm going to do and why I'm doing this is basically Converge. While running Converge jobs and getting results, what I have noticed is it's difficult sometimes to get the data out to a platform like MATLAB, for example, where most of the time I do my data analysis of Converge job. There isn't really a say API, the application interface for Converge for that. So what I'm going to present today is I have written an API which is free to use and in open source for any one of our Converge users here to use, and it's on Python. So Python is also free, so you can just download that and just get your Converge data in Python, and that will be the technical computing platform. At least for me, that's the choice, and you can use it free. So that's the main motivation. I've seen that if you have this API, the application interface with Converge, you'll be able to do the data analysis more easily, more live. I will say live data analysis you can do, and you can share those results more easily and more quickly. So this is what I'm going to show today, a quick demonstration of that. And the format of this presentation is not usual like the presentation slide decks, if you will. Instead, what I'm showing today is called Python Notebook. So I'll go through a quick overview of what we are going to talk about. In the table of contents, you'll see there is an introduction section. I'll get you started with the code repository, which is the open source Converge Python API that I've developed, and now it's open for everyone to use. I'll show a quick demonstration how to load Converge data and how it is easy, so easy to actually load it, and go through a few examples on how to plot some very basic things or get some data out of it. In the remarks, there is more tips on how to get started. So with that, let's get started. So the abstract is already here, but the main idea is, why do we need an open source Converge user community? What I have seen recently from many researchers, particularly from Argonne, is they're using CFD with the data science. And the data science, everyone has their own preferred way to do it, probably MATLAB. But Python is one of the most popular scientific computing language, particularly for data science and analysis, and it's free. So I believe that with the Python, you can actually expand your data analysis and data science with more users, with more collaborators. You can collaborate more easily with others. So I have put a Python API, as I mentioned, Converge, in a web-based version control platform called GitHub. That keep the code, and you can download it directly from there, or you can actually fork it, and you can do other stuff if you are familiar with Git repository. So the idea here is to have collaborators and Converge users and Converge developers come together and learn from each other on advanced CFD data analysis further. Few more reasons. I'll give this. The CFD reports these days are more like a static slide, but I believe you can also present your data more like a weatherman's report, if you will, more timely, more accurate, and also it's more lively. You're doing the analysis right on your feet. So I'll give you a quick example. I have written a Python-based COVID dashboard last year in December 2020 using Python Jupyter Notebook, and with just one click, you'll be able to update that dashboard and see the latest data. So I'll just go through that quickly. So the link is already here. So this is the Python notebook I talked about. And I'll just go to this here, time series plot, the first wave of COVID, second and third wave right around the December in these 4 counties. And I actually got this data from the open source, again, with coming from Johns Hopkins COVID Research Center. And all this data should be up to date whenever you run the whole notebook. And I'll show you that. This is based on all the states, all the counties, and this was the date. And that was when I actually published this report. You'll see the time series plot. So we will do this, all those three of these things, but with today's date. Today, we are recording on 9th of September. So Johns Hopkins might have updated till 8th of September. So you'll see that. So I'll just click here, run all, and I'll just say run. And it's going to load all the data, get it from the Johns Hopkins data center, and then it's going to do the analysis behind it. And see, you'll see now, this is updated. These plots are updated till today. All this based on, okay, that's 8th of September 2020. This is showing the mortality rate in percentage. And that one is showing in terms of the number of total COVID cases. And you can see clearly first, second, and third wave coming to Los Angeles and all these cities, different cities. And this is finally the new daily cases per 10,000 people in US as a whole and all these different counties. And so where do you think this is happening? The code is already here, actually. So if I click the show code, this is the code behind it. And some of this is so one-liner that it's almost like it's almost so easy to actually get the data from this one-liner. It is basically showing the mortality rate in percentage and on last 3 days, and that's all. I'm using Pandas, which is the most popular data science tool on Python platform to do this analysis. So let's go back to my presentation here. So what I was just showing is just one click, you just get the latest things in your report, and that's why not that kind of thing for your CFD report as well. The code lives with your report, so you don't have to worry about where the code is and where the report is. It just is in the report. You just have to show code. Again, I mentioned that easier to collaborate. Peers like your team from test data, test engineering can share their results, and you can just plot them here, do the analysis with your Python code. I mean, Converge Studio is a very good API as well that I have myself, and I've seen many of my colleagues use their own MATLAB-like or something like Python-like API just so that they can interact with other collaborators and peers so that they can bring in test data, they can bring in other simulation data, maybe 0D, 1D. You can share this code, the whole report with some external collaborators or Converge developers, like simply using share, and you just copy the link. And this is one of the thing I will do after the presentation. We will have the link to this. You can play it around yourself. The final thing I do is I actually run in Mainspring Energy, which is where I work, run my analysis in cloud platforms, like in Google Cloud Platforms or AWS. And actually, I do analysis while the simulation is running. So that with, let's say, for example, if you see emissions going up certain numbers that you don't like, you can stop that. And you can have well-managed HPC job. It's more like an algorithmic-based high-performance computing job management you can do. If certain numbers are hit, you can stop that and you can go with the next simulations, or you can let the Python Jupyter notebook, or you can write up a quick Python code to say which are the simulation jobs to run, and based on what criteria. And if the criteria is met, just stop it or go and run the next one, which you can also set up using Python. So I will get started with some examples here today. So I'll show how to get, what's this repository look like. So I'll just click here and show you the repository. It's basically an open source, as I mentioned here. There is a test example here based on Converge's own benchmark test data. So this is not mainstream's, the linear generator that we produce. This is not that data. This is actually a standard diesel case that's already coming with the repository because it's publicly available. And then there are a few of this where I have the packages. That's the API is managed inside this. I have written a quick introduction on how to actually get started here in this repository. You can go through this, and the presentation here will hopefully help you on that. But let me show you the test example. It has basically all the .echo files and .out files of the time series data. So let's go back to here. I'll going to clone that repository. And the cloning the repository is, you can do that also very easily by just going here, code. You can download the whole thing, or you can clone it. And I'll show it later. So here at just one click, I'll just start cloning the repository here. This is happening in the Google Cloud platform, basically. This platform is called Google Collaboratory. So now that the repository is cloned and it's the project initialized, I can start with my demonstration of loading Converge results. One thing to note, though, you do not need to do this cloning every time. It's just one time you need to do. If you're using particularly an IDE, which is a development environment, interactive development environment. I'll load the data and I'll interact with the data right now, and I'll show you how to do that. With few one-liners. For example, we need to import the necessary package, and there is only one package that I'll show you to import that, and then load an example benchmark CFD case that I mentioned about before. And then I'll show some plots of time series data of this example CFD case. So let's load the import, and let's import some packages, Python packages. So this is, once it's loaded, it shows symbol here. That means it's loaded here, and it took almost 0 seconds here. Now you're there to do all your analysis here. This package is what the open source API I mentioned, and that's in the repository. Now you can instantiate an example case so if your results lives in a project directory / project name like directory, project dir / project name directory, with all the .echo file and .out files, like your thermo files or all your .echo files. You can instantiate using just one liner. The CFD case here is the class that I actually imported as a package. So I just said that CFD, now it will become CFD object, and I'll just run it. So I'll just show you the code. It's done already. So example, for example, equals CFD case is project directory and the project name. That's all I did here. So example is my Python object that contains everything you need to load the data and do processing, data analysis with it. So now I'm going to load it, and it's only one line, just the CFD object here. In this case, it will be example.load _ CFD data, and that's it. So let's load it. Let's take. So it's loading all the thermo files, turbulence files, and all the .out files that I mentioned in the method, and it's done. It took 7 seconds. And that's it. Everything is there. I'm going to show, and I'm going to just create a code block here and show how it looks. Just for example now. So let's say I want to see the thermo.out files here, and this is that. Thermo.out file have all these columns with pressure, max pressure, mean pressure, all the columns. And you just have that as a table format with crank angle time. And this is what is happening behind the screen, like the package that I've developed can do this. It loads all the data, and that's it. So let's say if you want to plot the pressure itself and plot against crank time, that's it. You say just dot pressure dot plot, and you have the plot of pressure against crank angle time. So let's go through a few more examples like this. You want to know the RPM from the engine dot echo. So that I'll show you time series of the in-cylinder pressure trace just like that, and then there will be some more like PV diagram, in-cylinder emissions. I'll show some interactive examples as well. So let's plot the pressure trace I mentioned before. I've given a title pressure trace here, and you can do some simple algebra here, like multiplying by 10 gives you pressure in bar instead of megapascal, because the unit we get is, let's say, example thermo.al.units unit of pressure we get from the thermo.out file is in megapascal. So you need to multiply by 10 to get in bar. And you can do it and then plot it directly in one line. If you want to know all the units of all thermo files, that's there. You can see the heat release rate is in joules per time, things like that. You want to know units of turbulence, .unit. So this is all turbulence.out files unit. You will have that here. So you want to know, for example, what's the unit of TKE should be meter square per second square. There you go. So you have all those things in this object. The data is already in the object. So you can do simple multiplication and plot it like that. You can also get echo files, metadata, like I mentioned. Engine.echo has RPM. So it'll just say the object file dot, and then say get echo file. I have a underscore behind it. It's a private private method instead of public. And then you say file name and the file engine information that you are looking for. So this one will give 1600 RPM. I can give you another example of get echo information of file name echo, and then we can do engine info of SWOR. Let's say we want to know the SWOR, the initial SWOR that we have given is 0.978. And it could be for any dot echo file. It doesn't have to be engine.echo files. So that's the interface for that. Let's get some PV diagram done. It's simple. Again, one-liner, thermo.al plot an X volume and Y is pressure, and that's that. And it just made the scale log. And then you get the PV diagram like that. Let's get some species of like from the example dot species dot all. There are a lot of species here. You can see all this. So let's get some of them plotted out, and I'm going to do that interactively today. So let's plot OH with the formaldehyde. We'll see the formaldehyde is really near the time of cool flame chemistry, and then followed by the OH here. You want to, while you're plotting this, you want to change and see something else. For example, you want to plot CH4 and I don't know, maybe formaldehyde again. But let's see how that goes. You just click and change whatever you want. So one of my favorite to look is O2 versus CO2. Those are major species though, but still. The O2, the reaction happens, then that went down, it's still a reaction, and the Lin reaction, Lin combustion, and then CO2 gets formed, and you get that against crank time. Let's say you want to, so this is more interactive, right? And it's once you wrote this report and send it out, you give the option to drop down menu and just plot anything you want out of this. And it just took basically 2-liners like this: CFD object species.all, then I just mentioned OH, and then plot them. And you can, in the same plot, you can plot other species as well, like this. You can plot other simulation data like this if you are putting in the same axis. So it's that easy, just 1-liner. Once everything is loaded to an object like this, Python object like this, it's just 1-liner most of the time for analysis. So with that, I'm going to show another interactive plot of emissions of here the reaction phi versus maximum temperature of in-cylinder maximum temperature, and I'm naming that emission trajectory. So if you remember the famous plots of where the NOx island is and where the soot island is, you want to avoid those islands. This is almost like a flame temperature against the reaction phi. Some people want to plot it not against the max temperature, but maybe mean temperature. That's the bulk average temperature of the cylinder. Then just click down there, mean temperature, and the plot is changed directly. You can change it a different time, crank time. You can have more time to see how this emission trajectory evolved, and it will see that came down. It's a slider bar. It's a drop-down menu. It's more interactive. It's the code. The whole presentation is more lively instead of a static slide, right? That's what I want to mention here. So quick pointers, there are some pointers like all your thermo files, the thermo data is in your object.thermo.all. If you want to access thermo underscore region 3, for example, that will be under CFD underscore object thermo region 3. In this case, we have only one region, so I just had thermo.all in the example, but it will be automatically looking for all thermo files and put them together in this manner. And you can access in this way. If you have multiple restarts, don't worry about it. The pandas behind this thing take care of it. If you have thermo1 underscore region 0 and thermo2 underscore region 0 and then thermo underscore region 0, they will all get all get loaded into the thermo dot whatever the regions are .all files, and it will be on their order. Try them out. I want to show one more quick thing here. For example, let's say CFD, you define CFD object based on example here, and then let's take the CFD object and let's play with pressure trace again, or heat release rate. And you want to plot them. Let's plot them. You see that, that's great. But this heat release rate is more relevant between, say, -10 crank angle and maybe +50 crank angle. So that's that. And you just mention that it's now plotting your data between -10 and +50 crank angle. But you see there are some kind of noise here because grid snapping and things like that. And you want to get rid of that. And you probably go ahead and do that, all that analysis. And this is the power of pandas, not just, I didn't do anything here. Just the pandas is really good at doing this kind of things. You just do a rolling average. We'll probably do this way, the rolling average with a window of window type. I'm just going to give just simple window of maybe 10, and I'm going to take average of that, and then I'll take maybe between -10 and 30 or maybe 50, then plot them in the same plot as before. So I'll just go access, and then here in the same plot I'll just say access that, and you have those two together. And you can play with it even more on level raw, and this is smooth. and you can just legend, you see that there. And so, I mean, you can do so many things, and simple things like this, you will be able to get much better data analysis done here. So you can see this, the raw curve look like that, and the smooth curve look like this, and that's that easy. Similarly, I mentioned also like just the thermal file, but all the mixing file related data will be also here. I mean, if you just do mixing, and you will do that, and you will have all those things here. I think I'm on the end of my presentation now. If you have questions, definitely can send me an email, but you can get started by just installing Git and get Git cloned. You can use open source data science toolkit at Conda, or you can use integrated development environment like PyCharm. Contribute, join us, and hopefully you will find this useful. With that, I'll end this presentation now. Thank you very much.